Hi, good morning everybody. In this video, I'm going to go over the Kruskal Wallis test. The Kruskal Wallis test, I'm going to demonstrate using this data that you see on the screen. Let's say that we got different populations. We measured their happiness with pollution, with limited pollution, medium pollution, and high pollution. We took these measurements in places where there is no pollution at all, and with very limited pollution to high pollution, and we somehow got a metric for the happiness of people living in those geographical regions with no pollution to limited pollution to medium pollution to high pollution. And we got these measurements. We have a numeric value for all these measurements, and we want to find out whether pollution makes a significant difference or whether there are statistically significant differences between in the happiness levels with different amounts of pollution. So you might ask, why are we not using the ANOVA test in this case? As you recall, ANOVA test requires a lot of conditions, and one of the conditions, for example, is that ANOVA requires that the variances of different groups in the sample are homogeneous. We have done the Levene's test in the past. Levene's test either confirms or rejects the homogeneity of variances assumption. So if you take this data and if you run the Levene's test, for example, you can plug this into R, or you could do that in Excel. If you do that, you would notice that the homogeneity of variances assumption is violated. That's not met by this data. If that is not met, then it's not a good idea for us to do the ANOVA test. As a result, we'll go with what is a non-parametric test. And the non-parametric Kruskal Wallis test is very similar to ANOVA, but it's non-parametric, and you can use that when the ANOVA assumptions are violated. So that is the motivation for running the Kruskal Wallis test. For some of the business data, you will run into this situation where you will not be able to run the ANOVA test because ANOVA assumptions are violated. So then you would go to these rank sum tests, and one of them is this Kruskal Wallis test. So this is very, very similar to ANOVA, but the way that we conduct this test is completely different. So please bear with me. I would go through the example using a multi-step process on how we conduct this, the Kruskal Wallis test. So I have on this sheet, I have the same data that we had seen. So in step 1, what we do is we'll find out the rank of each of these values. We have 20 observations in each group, so altogether 80 observations we have in this, and all these 80 numbers we will rank order them. We'll give them a unique rank based on how they are sorted among these 80 numbers. So how do we do that rank order in step 1? We use a formula. That formula is equals if is number rank dot average A2 $A$2 colon $D $21 comma 1, right? So so what we are doing here is that we will get this. So if I look at this formula here for G2, this is the formula. A2 is the corresponding A2 is the corresponding number. So we are trying to find whether this number, whether A2 is a number or not. We don't have an issue with that. All our 80 values here are numbers. If it is a number, find out the rank of this number among all these um, 80 numbers. So that's what this is doing. The rank dot avg function is doing that, and we are finding the rank among these 80 numbers, and that range is always fixed because we have to go from A2 to D21. That's why we are using these dollar symbols here. And if it is false, if the number is not, if A2 is not a number, then we don't want anything to be shown. But in this case, it's a moot point because all these are numbers, right? So we do that, and we have extended this formula for all these for all these 80 numbers. So if you look at these, all these 80 numbers will get exactly one rank using this formula that's extended. Then in step 2, we compute the sum of ranks. So if you look at row 22, the sum of ranks, we add up all the ranks for no pollution. Similarly, we do the same thing for all the other groups. We have all these ranks added together, and then the group size is simply a formula count of G2 to G21. That's what we have in row 23. Each group is 20 measurements in this case, but sometimes the groups may be dissimilar in their size. Some might have 20, some might have 18, so it doesn't matter. Just get the group size exactly here. Now, after that, we square the ranks. In row 24, we square the ranks. So if you look at this, the formula here is G22 square. We square the ranks and we divide by the group size, and then that's what we do in step 4. In step 5, we take this formula. Before I come to this formula for the H value, let's look at the total number of observations. We know that the total number of observations is 80 here, and the total number of groups is 4, and the degrees of freedom, df, in this case is 3 because we have 4 groups, and we can use this formula count of G22 to J22 minus 1. So we have the degrees of freedom here. So the H value is uses this. So we have 12 times K24, which is K24 is the sum of all these R square by group size. We have this divided by B23 times B23 plus 1, which is the total number of observations. B23 is nothing but the total number of observations, which in this case is 80, minus 3 times B23 plus 1. So this formula is fixed when you do the Kruskal Wallis test. Once you compute the H value, we are going to compute the critical value. The critical value is obtained by chi-inverse function. Chi-inverse function takes the significance level as the first parameter. In this case, the significance level is 0.05, and it takes the degrees of freedom as the second parameter, and it computes for that significance level and for those degrees of freedom what should be the critical value. So we get that in G29 using that formula, and the p-value is obtained by this formula, chi-square distributions, by using the H value as a parameter, and we are also going to use the degrees of freedom as a parameter, and we obtain the p-value. So in sum, what we had done thus far is that we computed the ranks for each of these using a formula. We added up all those ranks for each group, and we squared those sum of the ranks, and we divided by the group size. So we got these, and we added up all these, sum of all these R square by group size in K 24. And after that, we used three formula to compute the H value, critical value, and the P value. And this P value is the one that we use to either accept the null hypothesis or reject the null hypothesis. In this case, since the P value is less than 0.05, we conclude that there is sufficient evidence to reject the null hypothesis. That is, that the happiness is does vary. There is statistical significant evidence that the happiness does vary by the amount of pollution among these four groups. But just like ANOVA, Kruskal Wallis will not tell you which of these groups have statistically significant differences. So what we have to do is to conduct once again post hoc tests. The post hoc tests that we see are in the next worksheet. So let me go to the next worksheet. And the post hoc tests also follow very much the very much based on the formula that we have here in these cells. For the Kruskal Wallis post hoc tests, we basically go through the same very similar process and very similar procedure to other post hoc tests, but we have to do the formula by ourselves in Excel at least. So we got all these four groups once again. We got the sum of all these ranks. I copied and pasted these, or I obtained these from the other sheet using formula. So I added them all up. Now we compute the average rank. The average rank is obtained by the total sum of all ranks in that group divided by the number of observations, which is 20. So the average rank is computed in row 24, B24 through E24. So if we are going to do pairwise comparisons on all of these tests, on all these groups, group 1, no pollution, limited pollution, no pollution, medium pollution, and so on and so forth, we are going to get this alpha value of 0.05. Number of groups is 4, and the number of comparisons is 12. So these, how do I get these 12 comparisons? In this case, the 12 comparisons are arising because in this example, we are going to do the one-tailed comparisons. So each tail is considered a separate comparison. So that's how we get the 12 comparisons here. And then we are going to divide this 0.05 by 12 for the significance level. So we get this in B30. This Z value is obtained by taking by using this function and 1 minus B30. That's how we obtain the Z value, and then n times n plus 1 by 12. This is 80. We have 80 observations. 80 times 81 by 12. That's how we get 540. So the critical value of difference is, in this example, all groups are equal sizes, so we are fine with this type of formula. So we get this, we use this formula, absolute B31 times square root of B32 divided by times 1 by 20 plus 1 by 20, because each group is 20. If you don't have equal groups, then for each pair of groups you are comparing, the critical value will have to be different. Suppose you have 20 in one and 15 in another, so you'll use 1 over 20 plus 1 over 15. So we have this critical value of the difference. Now what we do is, if you come through columns G through N, we got the group sizes, and then we got the average R, and the first version of the post hoc test, all pairs comparisons. I'll go through a couple of versions. So if we take no pollution, limited pollution, we know that the group average is for no pollution is 46.35. We have a formula here to do that, and limited pollution is 44.15, and then the difference in the average R between these two is 2.2. In column L, we take the absolute value of the difference. For example, if it turned out to be minus 2.2, we get the positive value, which is the 2.2 here. Then the critical difference is what we computed in B33 by looking at 0.05, the number of comparisons, and all this formula. So that is what is copied here or replicated here. We compare the difference and the critical difference using this formula, right? So if L9 is greater than M9, which in this case is not, then it would have been true, but in this case we have 2.2, 2.2, 19, 0, 16.8, 16.8. So all these differences are turning out to be false. So what we are saying is that group 1 and group 2, none of these groups, when we compare them, they don't have statistically significant differences. So that looks a little bit odd for us, because the Kruskal Wallis test did indicate that there is statistically, the evidence is leading to statistical differences among the groups. So we conduct post hoc tests, a second version of these post hoc tests, where we only take 3 comparisons: no pollution to limited pollution, no pollution to medium pollution, no pollution to high pollution. So if we just do these 3 different tests, then we do with these 3 tests, we do get the alpha value of 0.05 with 3 comparisons. Our critical value, our significance level is 0.008, and then the z value, we compute the z value to be 2.39, and the critical difference now using this formula, very similar to what we had done in B27 through B33, but now we have just 3 comparisons. So that's what the key difference is. So in B44, the critical value for difference turns out to be 1759. So with these, the group 1 and group 2, with no pollution, limited pollution, we get these average R. We go through all these, and the difference we get here, we get that here, and the absolute difference we get that here, and the critical difference is what we get for based on the value in B44. So if you look at these, the no pollution and high pollution, we do get the absolute difference of 19. 19 is greater than 17.59, the critical difference. So we conclude that there is statistical evidence that no pollution and high pollution have statistically significant differences in based on this analysis. So if you are conducting this for any other data, what I suggest is that you start with this Kruskal Wallis. You can use very similar format, and you compute the rank orders using essentially the same formula, and you find the sum of ranks, group size. You could use the same formula for your data, and if you plug in your data, in most cases this should work. Depending on the size of the data, you might have to change this template a little bit here and there, but otherwise this should give you a very systematic method for you to compute the Kruskal Wallis test as well as Kruskal Wallis post hoc tests.